Hey, budding number crunchers, welcome back to Numerical Analysis. It's Sunday, April 5th, and I wanted to take a quick minute and look over the practice problem that I left you with at the end of our previous video. So here it is. We wanted to look at this uh, uh, ODE here, initial value problem, and basically set up the degree 2 Euler's method for this problem. So the essential step there is finding the form of the Taylor polynomial that you use as you step through the problem. Uh, and then we wanted to do that and then go ahead and step through the first two or three steps of the problem here. One thing I forgot to mention is the step size, but we'll just use the same value we've been using up to now, that delta t of 0.1. So let's see what that involves. To find the second degree Taylor polynomial, we need the second derivative of our solution. Now, of course, the initial value problem gives us the first derivative, but we'll need to work with that to get the second derivative, and we do that in the usual way, just by differentiating the ODE here. So the second derivative is the derivative with respect to t of this first derivative, and you use the chain rule when you take the derivative of negative x cubed, right? So the derivative is negative 3x squared times dx dt. And then the derivative of 2t, of course, is just 2. And then use what we know about dx dt, namely that it's negative x cubed plus 2t from the original ODE, and simplify that a little bit. And so that's our second derivative. And then from this information, we're able to put together that second degree Taylor polynomial. Now, this is kind of a more general version of the Taylor polynomial, because we want to find the polynomial at any given step of the Euler's process. So we assume t is t sub n and x is x sub n, where that's the values that we've arrived at, at whatever step we're in during Euler's method. And so we just use those values in that derivative information. So, the second degree Taylor polynomial is your function evaluated at the current time plus the derivative of the function at the current time times t minus tn, and then 1/2 the second derivative evaluated at the current time times x minus, sorry, that should be a t right there, t minus tn, the quantity squared. So, this is a Taylor polynomial centered at t equal t sub n. And then for these values x of t sub n, well, that's just our solution, at the current step, x sub n. X prime of tn, we get that from the ODE here, with x equal to x sub n and t equal to t sub n. And so that's where this minus x sub n cubed plus 2t sub n comes from. That's just our x prime at tn, still times t minus tn. And then 1/2 the second derivative. Well, we just computed the second derivative here. And so again, when we're at step tn and xn, you plug those values into our second derivative, and we get this for x double prime of tn, and then times t minus tn, the quantity squared. So that's our Taylor polynomial that we're going to use at each step. And what we'll simply be doing at each step, we'll be using the current values of x sub n and t sub n here in that Taylor polynomial. So let's go through the steps. Step 0 simply is initializing the t and the x. So t0 is 0 and x0 is 1, and that comes from the initial condition. Step 1, we first compute the Taylor polynomial of degree 2. So here's just the formula we came up with on the second slide, or the slide just previously. And I'm going to now plug in, and notice the index here is n equals 0, because that's the solution step, the latest solution step that we know. And now I'm going to plug in what I know about x sub 0 and t0. And so I'm just doing that here. And so you wind up with 1 minus t plus 5/2 t squared. And then once you've got the Taylor polynomial, you can just project forward to the solution at the end of this step, of step 1. So t1, you just increment your current t by the step size, which we're taking to be 0.1 here. So we'll just get 0.1. And that should be x1. That is just take your t1 and plug it into the Taylor polynomial. So we have p2 of 0.1, and so just plug in 0.1 to this guy and you get the 0.925. For step 2, we begin again by computing the Taylor polynomial, this time centered at the solution we just arrived at the end of step 1. So now I've got, it's this same formula here, except now I'm using n equal 1, right? So I'll have x1 and t1 plugged in here. And so x1 minus, there's our first derivative evaluated at t1 and x1, times t minus t1. And then 1/2 the second derivative, and that's again from this piece right here, evaluated when with x1 and t1. That should be a t1 right there. Sorry for all the typos. But we're plugging in t1 equals 0.1, x1 equals 0.925 to these expressions, and you get this. And then to project forward, first increment your t value by adding delta t to it. So we now get 0.2, and then plug that t value into the second degree Taylor polynomial that we just came up with. When you do that, you get 0.88345. So the solution we've gotten this far, I've just tallied our results from steps 0, 1, and 2. Here we go. And we can, of course, write down the interpolant for the solution just by recording the Taylor polynomials at each step. And this, again, is going to give us a more accurate picture of the solution than simply just connecting these pairs with straight lines. In fact, I went ahead, as usual, and computed the solution for 10 steps using MATLAB. Here it is in color, and in between each of our computed solution points, I've used the interpolating function to connect the dots here. And you can also see the exact solution computed using a much more precise numerical method. And so again, we're pretty close here with this second degree Taylor polynomial in Euler's method. So I hope that helps with your next homework. It will be posted pretty much simultaneously with this video, so you'll see it today. And that'll be due Monday at 11 o'clock. As always, if you have questions, let me know. And I hope you're doing well. Stay tuned, stay in touch, and stay well. See y'all soon.